8 बजे का समय हो चुका है। अगर लाइव आ चुके हैं तो मैसेज करें आप लोग, हम कंफर्म हो लें कि कौन कौन से लाइव हैं। मेरी आवाज़ जा रही है आप लोगों तक? आवाज़ जा रही हो तो मैसेज करें आप। अगर मेरी आवाज़ पहुंच रही है तो आप लोग मैसेज करें। कुछ तो है कनेक्टेड। कनेक्शन तो हो रहा है धीरे धीरे, आप लोग आ जाएं। आज बायो एनर्जेटिक्स का जो नेक्स्ट टॉपिक है, नेक्स्ट पार्ट है उसका, और वो काफ़ी इम्पोर्टेंट है आपके एग्जामिनेशंस के लिए भी और आपके नेट के लिए भी। मेरी आवाज़ पहुंच रही है आप लोगों तक? आवाज़ पहुंच रही है मेरी आप लोगों तक? ठीक है, ठीक है, ठीक है। तो फ्री एनर्जी, आज हम लोग नेक्स्ट टॉपिक पे हैं, दैट इज फ्री एनर्जी ऑफ ए सिस्टम। किसी सिस्टम का फ्री एनर्जी क्या है, उसको कैलकुलेट कैसे करेंगे, फ्री एनर्जी का सिग्निफिकेंस क्या है, व्हाट इज द सिग्निफिकेंस ऑफ द फ्री एनर्जी, व्हाट इज फ्री एनर्जी, एंड व्हाट इज द मेथड फॉर द कैलकुलेशन ऑफ द फ्री एनर्जी। तो फ्री एनर्जी को लास्ट क्लास में मैंने बतलाया था कि ए लीनियर कॉम्बिनेशन ऑफ थर्मोडायनेमिक फंक्शंस सच एज इंटरनल एनर्जी इन ई, enthalpy H and entropy S is state functions। इसको हम बोलते हैं कि जो स्टेट है सिस्टम का, उसके ये देयर आर 3 functions of any state, that is internal energy, enthalpy and entropy, and such a combination is known as thermodynamic potentials। इसको, इस कॉम्बिनेशन को वी आर सेइंग द थर्मोडायनेमिक्स पोटेंशियल, एंड द two functions, the potentials, the thermodynamic potentials can be analyzed by the two methods. One is the Helmholtz free energy and another is the Gibbs free energy, and the both represents the thermodynamic potentials। ये जो दोनों कंपोनेंट्स हैं, दे रिप्रेजेंट द थर्मोडायनेमिक पोटेंशियल्स, इन विच गिब्स फ्री एनर्जी इज मोर सिग्निफिकेंट फॉर द बायोलॉजिकल सिस्टम, फॉर द स्टडी ऑफ द बायोलॉजिकल सिस्टम और फॉर स्टडी ऑफ द लिविंग सिस्टम देन द हेल्महोल्ट्ज फ्री एनर्जी। बट हियर आई एम going to describe in very brief in the Helmholtz free energy, and Helmholtz free energy represents the relationship of the free energy, that is the internal energy minus temperature multiplied by entropy। That is, if we consider that the F free energy is represented by F, capital F. Internal energy is represented by E, as we discussed earlier, and temperature is represented by T, and entropy is represented by S. Then the relationship is represented as F बराबर E minus Ts. But here we want the change in the free energy. That means when a system receives some energy and upgraded to another system, stage of the another system, then the change of energy, change of free energy is represented by delta F. Likely the E, that is the internal energy of one system, is converted into E1 to E2. E1 से E2 की ओर चला गया. Change of the energy, that is represented by delta F. T1 is converted into T2 in another system, and S1 is upgraded to the S2 in the another system. So, if we want to calculate the change in the free energy, that is delta F, that means the delta F, F is represented by E minus Ts, then delta F, we calculate the delta F by the these combination, the two systems, system 1 and system 2. That means E2 minus T2 S2 minus E1 minus T1 S1. That represents the delta F. So the delta F is represented by change of energy, that is delta E. Now the system energy change from one system to another system, or from system 1 to system 2, is represented by delta E minus T, and the change in entropy is represented by delta S. T is not represented any change, because in last class I said that in the living system we are present in isothermic condition. So T is not changed here. So the delta F is equal to delta E minus T delta S. It is the relationship of the free energy from two systems in the condition of the Helmholtz free energy. Here, it is necessary to remember that the decrease in the work function, that is F, is equal to the maximum work done by the system. It is clear from the relationship that the decrease in the work function F is equal to the maximum work done by the system. That means the energy is consumed in the work. So that particular level of the energy is decreased from the work function F, or that is work function F, that is the free energy, that is decreased here. Hence, the quantity is termed as work function, because the energy, free energy consumed in the work done is reduced. So the energy reduced or the energy decrease is referred as work function. Now we come in the next topic, that is the Gibbs free energy function, and it is important. It is necessary to understand properly the Gibbs free energy function. The Gibbs energy function is represented by capital G. Symbolically, it is represented by capital G, and G is represented as heat content or heat content, that is referred as the enthalpy, minus temperature into entropy. It is the relationship of the Gibbs free energy. In the Helmholtz free energy, that is the relationship F barabar E minus Ts, but in the Gibbs free energy, we consider the relationship as heat content, that is enthalpy, heat content is referred as enthalpy, minus temperature into entropy. If the enthalpy, as also we discussed earlier, that enthalpy is represented by capital H and entropy is represented by capital S. So the relationship is represented as G barabar G equal to H minus Ts. T represents here, T represents the temperature. Now we want to calculate the change in the free energy, change in the free energy or change in the Gibbs free energy. As we observe, the differences is represented by delta. So here the change in the Gibbs free energy is represented by delta G. Then here again the two system. In the system 1, the enthalpy is H1, the temperature is T1, and the entropy is S1. But when it accelerated or it comes in the second system, then the enthalpy of the second system is represented by H2, temperature of the second system is represented by T2, and entropy of the second system is represented by S2. So here again, if we normalize the equation, then the dg, that is the change in the Gibbs free energy, is represented by S2 minus T2 S2 whole in bracket minus H1 minus T1 S1. Here again the T is not changed because the system is isothermic. So, and the change of the enthalpy is represented by delta H, and change in the entropy is represented by delta S. So the relationship now is delta G equal to delta H minus T delta S. It is the relationship and it represents the Gibbs free energy. Now, if we consider the delta G equal to delta H minus T delta S, then if we want to calculate the value of entropy in the form of the Gibbs free energy, then delta S, if you equalize it, that delta G equal to delta H minus T delta S is rearranged in the form of the entropy delta S, change in the entropy, that is the delta S. Now the delta S equal to delta H minus delta G divided by temperature, that is the T. It represents the change in the entropy. Now if we reorganize the equation, that is the relationship which we considered here, that is delta G equal to delta H minus T delta S. One way we we derive the formula for the derivation of the, or for the calculation of the differences or change in the entropy. Likely, if we reorganize the relationship to calculate the change in the enthalpy, then delta H equal to delta E plus P delta V. Now the relationship delta H equal to delta E plus P delta V we developed the same equation in my last online video or live video last day. So the relationship for the enthalpy and entropy which we are obtained today are same as we observed in the last day. Now, if we reorganize the delta G after the derivation of the formula or after the derivation of the enthalpy, delta H बराबर delta E plus P delta V is one equation, and delta G equal to delta H minus T delta S is another equation. Now the equation is reorganized as the delta G equal to delta E plus P delta V minus T delta S. Now it is the relationship we derive today for the Gibbs free energy. So here we obtain the three relationships here. One is the delta G बराबर equal to delta H minus T delta S. Another is the delta S equal to delta H minus delta G divided by T. Another is the delta G equal to delta E plus P delta V minus T delta S. If we want to say in the language, then the Gibbs free energy is equal to the change in the enthalpy minus temperature of the system multiplied by change in the entropy. In second, change in the entropy is equal to the change in the enthalpy minus change in the Gibbs free energy divided by temperature. Third, change in the Gibbs energy equal to change in the internal energy plus pressure multiplied by change in the volume minus temperature multiplied by change in the entropy. And these are the relationships we derived from the functional analysis of the Gibbs free energy. Now, for a process occupying at constant temperature, for a process occupying at constant temperature and pressure, the change in Gibbs free energy is equal to the maximum useful work, and it is referred as W max, work maximum of any system. Now, the component which we are discussing here is used for the normal atmospheric pressure and normal temperature. And we well known that normal atmospheric pressure is 1 atm, is considered as 1 atm, that is 1 atmospheric pressure, and 1 atm is approximated equal to 760 mmHg. Likely the normal temperature is 0 degrees centigrade and it is equalized to 273.15 Kelvin. It is the normal temperature and normal pressure. Now, after the discussion on the Gibbs free energy function, we come for the discussion on the relationship between a standard free energy change and equilibrium constant. And we well known that the equilibrium constant is one of the important parameters in the reversible reactions. And in the biological system, we uh, studied a number of reactions has the reversible nature, having the reversible nature. And here, in last class, I also told that in the biological system, the energetics is related with the biochemical molecules and not directly with the heat. So the energetics of the biochemical molecules of any system in the biological system, in any biological system, the energetics of the biochemical molecules is more important and considered for the study of the bioenergetics in the living. And here, if we want to study the relationship between the standard free energy change and equilibrium constant, it is two. We studied two relationships earlier. That one is the change in enthalpy, that is the delta H, change in energy enthalpy. It is represented by delta H, and delta H is equal to change in the Gibbs free energy plus temperature, normal temperature, that is the temperature, multiplied by change in the entropy. Second, change in the entropy is equal to change in the enthalpy minus change in the Gibbs free energy divided by temperature. Both relationships we are discussed clearly. Now the standard free energy change, standard free energy change is represented by delta G naught. Naught is represented on the superscript of the capital G. That means it is represented the standard free energy change, and the standard free energy change of a chemical reaction may be defined as the free energy change when the reactants and products in their standard state. It must remember always that the standard free energy change, that is represented by the delta G naught, not by the delta G, but delta G naught, not that is represented by a small O or the superscript. That is the delta G naught of a chemical reaction. The standard free energy change of a chemical reaction may be defined as the free energy change when the reactants and products are in their standard state. That means the in the normal state, and it is represented by 298 degree Kelvin temperature and 760 mmHg pressure. Both are the standard state of temperature and pressure. Here, the standard free energy change, the value of the standard free energy change determines the nature of reactions. Nature of reactions. That means what kind of reaction is it? If the delta G naught, that is the standard free energy change, is zero, it represents the reaction is present in equilibrium state. Second point, if the delta G naught, that is the standard free energy change, is negative, if it is negative, it represents that the reaction is spontaneous. The reaction is spontaneous. And here there is no need to provide energy in the form of heat. That means the reaction is exergonic. Again, I am repeating that if the delta G naught, that is standard free energy change, is negative, it represents the reaction is spontaneous and it is exergonic. In third point, if the standard free energy change gives a standard free energy change, that is delta G naught, is positive, then it represents the reaction is non-spontaneous and reverse reaction, or the reaction is endergonic. These are the components and the facts we observed by the quantum or by the value of the standard free energy change, that is represented by delta G naught. And here the unit of delta G naught, that is the change of the standard free energy, is calorie per mole. Kilocalorie per mole is the unit of delta G naught. So, if we observe the biochemical reactions and we observe the standard free energy, and after discussion, it is clear that the biochemical reactions occur near pH 7. It is the basic difference that in the biological system, the biochemical reactions is commonly occurred. The biochemical reactions are commonly occurred around the pH 7. So, is conventionally designated the standard pH, like the standard temperature and standard pressure. We consider the standard pH for the biochemical energetic study that the pH is 7 in biochemical energetics. We consider the pH 7 for the study of the biochemical energetics. Now, the standard free energy change at pH 7 is represented by the symbol delta G naught dash. Delta G naught dash is used for the energetic change or change in the free energy at pH 7. These are the symbolic representations, and as I think that you all understand properly that what is the free energy, gives free energy, what is the symbol of the gives free energy, what is the relationship between among the enthalpy, entropy and gives energy, and what is the significance of the gives free energy in the rate of reactions or to determine the directions of the reactions in the biological system. Now, after the study and after the proper discussion, the delta G, that is the change in the gives free energy, had following significance, and the two significances are important. First, a reaction is dependent. When we consider the biochemical reactions, the reversible reactions means a reactant is reversibly responsible for the formation of product at the particular concentration, and the products again react to form the reactant. So an equilibrium is necessary, and for the determination of the equilibrium, the energetics of the biochemical reaction, the proper understanding of the biochemical reaction is necessary. And here the two significances of the gives free energy among in these two. First is a reaction is dependent only on the free energy. In the biological system, a reaction is dependent only on the free energy of the products minus that of the reactants. What is the free energy of the product minus what is the free energy of the reactants? It determines the reactions of the biological system. The delta zero, dg delta g of a reaction is independent of the path of transformation. There is no relationship in the released energy or free energy to the path of transformation of the biochemical molecules. It only determines the direction of the reaction. Second, the value of delta G, that is the Gibbs free energy, gives no information about the rate of reaction. It only determines the direction of the reactions. It cannot determine the rate of the reaction. So, if we consider aerobic oxidation, I am just giving an example, and if we consider aerobic oxidation of glucose, that is C6H12O6. Oxidation means that is the biological combustion of glucose, that is by the use of the 6 units of the O2. Then the C6H12O6 plus 6O2 is converted into 6CO2 plus 6H2O. It is well known reactions, and that is we all study or we all know it is the reactions associated with the respiration. Then the reaction, if occurred at the standard temperature and standard atmospheric pressure, standard temperature that is 290 kilocalorie, and atmospheric 1 atmospheric pressure that is the 760 mmHg. And here the change in the free energy, because you all study that the 1 unit of the glucose after complete combustion or after complete oxidation produces 686 kilocalorie energy. That is the change of energy. It is the change of energy. That is the delta G. The value represents the delta G value, because it does not represent the path, because in the full combustions of the glucose there are a number of biochemical reactions we all studied at the intermediate level or at the graduate level. So here the 1 unit of the glucose after the complete combustion or complete oxidation produces free energy, that is the change of the energy of the system, is the 686 kilocalorie. That is the delta G. The value is the delta G. And here the value of enthalpy is 673 kilocalorie. The value of enthalpy is 673 kilocalorie. And for the data, if we want to calculate the value of entropy, then it is very easy. That we have the two components. We have already information of the two components. One is the free energy, another change in the free energy, and another is the change in the enthalpy. So the change in the entropy, that is delta S, is equal to delta H, that is the change in the enthalpy, minus delta G, that is the change in the internal energy, divided by T. Just we discussed the formula. And here, if we calculated the value, because we have information of the free energy, that is 686 kilocalorie, we have information for the enthalpy, change in the enthalpy value, that is 673 kilocalorie. So if we calculate the change in the entropy, then we calculate easily the 43.62 calorie per degree of temperature. That is divided by the 298. That means minus 673 kilo calorie. That is 673,000 minus 673,000, because it is the change, so it is represented in the form of the minus sign. So 673 minus 673,000 minus change in the in uh, change in the energy, that is 686,000 divided by 298. So the minus and minus is converted down, and we calculated the value in the form of 43.62 calorie. Or if we converted the calorie value in the form of a joule, so in last class I told you that one calorie is equal to the 4.184 joule, 4.184 joule. So if you multiply the 43.62 calorie and convert it into the joule, now we get the 184.096 joule. So the change in the entropy is we calculated easily by the use of the formula. And as I think that you properly understand the what is the entropy, what is the enthalpy, and what is the change in the energy, because I am just describing a formula in the form of the complete oxidation of the glucose molecule as we studied in the respiration. Now, in the next step, we want to discuss on the relationship between a standard free energy change and equilibrium constant. That here two things. One, we have already discussed in last day and in present day also, that the change in the standard free energy, that is delta G naught, that is the standard change in the standard free energy. Another component is here, that is the equilibrium constant. Then what is the equilibrium constant? Equilibrium constant, we all studied equilibrium constant in the reversible reaction and law of mass action. Here the ratio, and it is represented by Keq, that is kinetics at equilibrium. Keq represents the equilibrium constant. That if the reactant, suppose the reactant is A and B, and the reactant is reversibly responsible for the production of two products C and D. So K1 represents the forward reaction and K2 represents the backward reaction. That is A reacted to B to form C and D, and the forward reaction is represented by K1 and the backward reaction is represented by the K2, and the ratio of the K1 and K2 is represented by K equilibrium. And here the free energy, if we consider the relationship of the free energy with respect to the equilibrium constant and the free energy, what is the free energy? That is the delta G. Delta G represents the free energy. That is, the delta G is equal to a standard free energy change, that is delta G naught is the standard free energy, and the change energy is the in the In this stage, the relationship, if you want to determine the relationship of the standard free energy and equilibrium constant, that the equilibrium constant is determined by the RT log E, RT log E, C, molar value of the C multiplied by molar value of the D, that is the product of the molar value of product, मतलब multiplication value of the molar value of product divided by molar values of the reactants. And here the R represents the gas constant, T represents the absolute temperature, and molar value, we all know what is the molar value. So here the R, if we considered in the form of the constant, R is the gas constant, and if we consider the R in term of calorie, then it is 1.98 multiplied by 10 minus 3 kilocalorie per mole per degree. And if we consider the gas constant in the form of joule, then it is 8.314 joule per moles. So in this way, a relationship is, we observed a relationship between the change in the free energy and the equilibrium constant of any reversible reactions or in the biological reaction system. That is the change in the free energy equal to change in the standard free energy, that is delta G naught plus RT log E and multiplied by molar products of the products of reaction and molar products of the reactants. And if we use the symbolic, if you represented it by the symbols, that delta G equal to delta G naught plus RT log E molar value of C into molar value of D divided by molar value of A into molar value of B. It is the relationship between the standard free energy change and equilibrium constant. Further, if we study the relationship, it is clear that the standard free energy change, that is the delta G naught, that is the standard free energy change of a chemical reaction, may be defined as the free energy change when the reactant and products are in their standard state. It is the standard value change of any chemical reactions. Now, I am repeatedly say that the standard state is 298 calorie temperature at 1 atm or 760 mmHg pressure. Now, we all studied these components in the physical chemistry also. But here we want to differentiate some basic differences or differences in the applicability, not in the basic principle. Some the applicability of the thermodynamic principles is different between the physical chemist, is different for the physical chemist and biochemist. And what is the difference? It is necessary to understand properly here. It is important to first distinguish between the standard state implied by the physical chemist and biochemist. In physical chemistry, the standard state refers to the situation in which all the reactants and products are in unit molar concentration. It is the standard nature for the physical chemist. But in the biochemist and for the biochemist or in the biochemistry, we follow the same basic principle. There is no difference in the basic principle, except we define that the H plus ion that is responsible for the determination of the pH. And in the biochemistry, we follow the same basic principle, except we define the H plus ions concentration for the standard state to be 10 power minus 7 mole M molar value, because the physiological state about 7, because the physiological state of the biological system is about 7, we considered it also for the standard free energy state. It is the basic difference between the biochemist and physical chemist. Consequently, what is the effect? Consequently, the change in the standard gives free energy according to these two conversations will be different. It will be different. Now we refer delta G naught dash. When we consider the pH, then it represented by the standard gives free energy is represented by delta G naught dash instead of delta G naught in biochemistry. So, in the if we want to look after the relationship between the dg naught and dg naught dash, it is dg naught equal to dg naught dash minus 40 kilojoule per mole H plus ion. It is the relationship, it is the difference between the biochemist and physical chemist. Here the relationship dg naught represented the standard free energy at pH 7, and the relationship is dg naught equal to dg naught dash minus 40 kilojoule per mole H plus. So, if we analyze, of course, I am saying that the relationship between the free energy and equilibrium constant is dg equal to dg naught plus RT log E molar concentration of product of the molar concentration of products divided by molar concentration of reactants. This component represents the equilibrium rate, equilibrium constant. This is represented the equilibrium constant. Here we neutralize it by the calculation. So dg naught equal to minus 2.303 RT log K equilibrium. Kinetics is at the equilibrium. The molar the molar value of the products and the molar value of the reactants, multiplication value of the reactants are neutralized by the K equilibrium. So the formula or the relationship is simplified here, and dg naught is equal to minus 2.03 RT log K equilibrium, that is kinetic at the equilibrium. And now sometimes in the NET examination, not in your postgraduate examination, but of course in some universities in the postgraduate examination is posted in the numerically. Numerical questions are also asked, but in the net, the question is asked frequently. And for the calculation, for the simplification of the calculation, it is simplified further than the 2 point. The main formula is here. The main formula is dg equal to dg naught plus rt log e molar value of C multiplied by molar value of D divided by molar value of A multiplied by molar value of B, that is the product, molar value of the products and molar value of the reactants. So here it is simplified further and it is represented as the dg naught, the change in the free energy equal to extended free change in the extended free energy, uh, and here the dg naught is again simplified as the dg naught equal to minus 2.303 RT log K equilibrium. It is again simplified as at the 25 degrees centigrade 2.303 RT is equal to the 1364. The value, the numerical value of 2.303 RT, because it is the part, and thereafter if you remember it, so you simply put the value and get the total value of the change in the free energy. So here the formula is delta G naught equal to minus 2.303 RT log K equation. Then it is, if we observe at the 25 degrees centigrade, then the 2.303 RT is equal to 1364, but at the 37 degrees centigrade 2.303 RT is 1419, and in the form of Joule, 2.303 RT is equal to 5700. So if you remember the values of the 2.303 RT, then it is easy to calculate the value of the free energy in examination. Now I suppose that you all are understanding properly what is the relationship between the free energy, what is the relationship between the extended energy, what is extended energy, what is the free energy, what is the relationship between the kinetics and free energy, and the second law. If we consider the second law of thermodynamics, we all studied from the last day second law of the thermodynamics, that second law, as per the second law of thermodynamics, all naturally occurring processes proceeds in a direction that leads to a minimum potential energy level. It is the second law. Minimum potential energy level means towards the equilibrium. And likely, of course, the third law of thermodynamics is not applicable too much in the biological system, but just I am representing the third law of thermodynamics here. And the third law of thermodynamics represents that at a temperature of absolute zero, that is the 0 degree Kelvin, when all random motion ceases, that's all random motion ceases, the entropy of a perfect crystal of energy substance is zero. That it is the zero, that is all the atoms are maximally ordered. It is the third law of thermodynamics. So now I consider that you all understand properly what is the free energy, what is the Gibbs free energy, what is the standard Gibbs free energy, what is the relationship between the kinetics and free energy, and probably in the next class or tomorrow I will discuss on the coupling reactions related with the release, change of the free energy and release of the free energy, and what is the significance of the uh, coupling reactions in the biological system. So I think that you all are properly understand the concepts of the free energy today, and if you feel any problem, then you give me comment in my YouTube channel, and I will explain further when I find the time for that. So if you have any problem, someone is Deepak Kumar. Sir, we cannot get okay in practical. I can't understand what he wants to say. What he wants to say, I can't understand. Deepak Kumar, sir, we can't get okay in practical. I I am not in a position to understand that which type of question you ask. Sorry. Deepak Kumar, you are saying that, sir, we can't get okay in practical. What does it mean? I don't understand properly. Minus 40. Have any question? Have any questions? If any question, you give me message. If any, if anyone feel any problem in the proper understanding of the today topic, you give me question, or after that you are free to comment or ask any question on my YouTube channel. I can't understand the Deepak Kumar again writing that 0 Kelvin. What does it mean? What type of Kelvin? In biological system, the 0 Kelvin is not applicable, and it has the very limited source, and particularly it is considered for the study of the crystal for the physical bodies. So I am saying in my lecture also that the third law of thermodynamics is not more or not applicable for the system, and it is in the supercooling state sometimes and lies in the Arctic or Antarctic region for the bacteria. Any more? No one? Okay, thank you. Thank you to all. Now tomorrow we will discuss on the coupling part of the reactions, and after that we will discuss on the energy rich compound. Okay, thank you.